Everyone. Welcome to lecture 7 in this series of lectures on transformers. And in this lecture, we are going to see approximate voltage drop in a transformer. So, we had developed the equivalent, not the complete equivalent, but then we have developed the impedance of the primary and secondary of the transformer. And we have solved some problems in the lecture 6. But one thing we might have noticed there is that the complexity of the vector diagram. So we'd like to make some simplifying assumptions as typically the engineers do. We'd like to make some simplifying assumptions and try to make it simple to do the calculations and to understand. And the first assumption we make is neglect no load current of the transformer, that is I naught. So we know that I naught is the no load current of the transformer, which is about uh, I'll just write about like less than 5%, maybe 3% or so, less than 5% of full load current. So since it is less than 5% of full load current, if I ignore I naught, then what happens? So you look at it just by doing this one simple step. So what was I1? I1 is nothing but I naught plus I2 dash. So now because this I naught is neglected, so I1 is nothing but I2 dash, which is nothing but K into I2. So using this formula, we are able to find I1. By the way, so there is always confusion what is K, it is N1 by N2 or N2 by N1 and all these things. Just remember that high voltage side the current will be low and low voltage side the current will be high. Accordingly, you just multiply the factor. So just by making this, now if I draw the vector diagram, it looks something like this. So we have, I'll take V2 as reference. So this is the terminal voltage of the secondary side. And then I'll take I2 as the lagging current. So what we'll do, I'll add I2R2. This is the voltage drop due to secondary in the resistance, and I2X2. This is the voltage drop in the reactance in the secondary. So these sum together will be, so let me just move the label of, so this is V2. So this together, now I'll get E2. I'm not able to draw the straight line like this. Okay, so this is E2. Now on the other hand, because we ignore I naught, I can take exactly opposite. This is I2 dash. This itself will become my I1. And similarly, exactly opposite to E2, I'll get E1. So now to this E1, if I add the drops, so this is I1 R1 and this is I1 X1, then finally I'll get the voltages V. Now, just like how the I2 has been transferred, so I think let me just make it correct. I think this one here, I want to define it properly. So let's define K as V2 by V1. So if I do like this, then what will be the I2 dash? I2 dash will be I2 by K because this will be equal to I1 by V2, sorry, I2. If that is the case, then the I2 dash is nothing but I1. Yeah. So I think I have written correctly. So this is K into I2. Now what about the voltages? Now I want to transfer the voltage. What is E1? So what is the relation between E1 and E2? So again, for simplifying assumptions, I'll take E2 by E1 is equal to K. So E1 will be E2 by K. So this is nothing but E2 divided by K. So, so therefore, whenever the voltages are going from secondary side to the primary side, it is divided by K. And whenever currents are going from secondary side to the primary, I'm sorry, secondary to, so again, let me, voltage going from and to, from secondary to primary, then you divide by K. Whereas current, when going from secondary to primary, you multiply by K. So this is factor. On the other hand, if I transfer any voltage from primary to secondary, I have to multiply by K. And if I transfer any current from primary to secondary, you have to multiply by 1 by K. So this is just basically logic on working of transformers. So based on that, you will get this. So let me make some place. So I need some place here. So I'll just move this thing down. So therefore, what I want to do now is E2 and E1 are related like this. So E2 is E1 is E2 by K. Now to that vector, I am adding I1 R1. So this is the voltage. So this voltage will be parallel to I1. Or in other words, if I transfer this voltage from primary side to secondary side, it will be getting multiplied by K. So I'll get something like this, which I can add to E2. So this is K into I1 into R2, like this. Sorry, R1. So I1 R1 from primary side came to secondary side. It will get multiplied by K, and now I can add it to E2. So next I can add this also, that is K into I1 into X1. So this also the transformed I can add. Then this entire vector, so from here to here, so let me draw it like this. It's difficult to write a freehand straight line. Yeah, so this entire vector will be my E1. No, in fact, it will be V1. So like this, we are able to draw it. So not V1, it will be K into V1, like this. So that way, we are able to get because we have ignored the I naught current, we are able to do this kind of simplification. Now you just look at only this part of the vector diagram. So this I can once again redraw. So if I redraw it once again, so it will be something like this. So I have V2 here. Then I have I2 lagging V2. So then parallel to I2, I'll get this one. And then like this, I'll get, so this is I2 R2. This is I2 X2. So then this is I2 Z2. And this one will be E2. Now that I got E2, that I'll just, E2 is nothing but K into E1. So if the E1 I transfer to the secondary, it will exactly coincide with this. So therefore, to K into E1, again I will add one more resistance drop. This will be exactly parallel to this line. It will have the same angle. And then again, one more line like this. So this will be K into I1 into R1. This will be K into I1 into X1. This is K into I1 into Z1. So this total, now I get this new vector. This is V1. So like this, it becomes simplified. Not only that, you just, now I don't want to deal with E's. I want to directly deal with the terminal voltages. I want to get a direct relation between V2 and V1. So we can do that actually. So you look at this, this and this are in parallel. So if I just extend this, and if I extend this, so this also becomes a right angle triangle. So what is this one? This is KI1R1. So this entire resistive drop is nothing but I2R2 plus KI1R1. I'm sorry, this is K into V1, not exact V1. So, but what is I1? So this is total resistance drop. So that is I2 R2. Now what is I1? I1 is nothing but I2 dash, which is nothing but K into I2. So I'll get K square into I2 into R1. Here if I take I2 common, R2 plus K square into R1. And if this looks familiar, this is nothing but I2 into R naught 2. So if I refer all the resistance to the secondary side, then this quantity itself I can define as the voltage drop. Similarly, you look here. Just a minute. The current is transforming from primary to secondary side. If I just once again, by the same logic, if I just once again look at this part, so it is K into I1 into R1 plus I2 into, sorry, this is X1 plus I2 into X2. This is total reactance drop. And this one will come out to be I2 into X02. Of course, J will be there because each X has a J. So the relation will be 90 degrees leading I2. So now I have total voltage drop will be I2 R02 plus J I2 X02. So this is my total voltage drop. Or in other words, I2 into Z02 is my total voltage drop. So this is, if I know the voltage drop, then I can say V2 plus I2 Z02 will be equal to K into V1. So I can get this particular relation. All right. So these are terminal voltages. So now you see, uh, we can further simplify it actually. If you look at it, see, I have V2 again. So once again, this is I2 R not 1. So I'll directly write now R not 1, and this is I2 X not 1. Sorry, I'm sorry, R not 2 and X not 2. This and this point I am saying it is K into V1. So now if I draw the horizontal line here, and then draw a vertical line here, and then this one, if I just draw a circle taking this O and A as radius, if I draw a circle, let's say it intersects here at B. So the actual voltage drop, let's say this, call it OC, is the second voltage of the terminal voltage of secondary. OA is the terminal voltage of the primary with multiplied by K. So the actual drop I can find uh, is from C to B, but then I'll just approximate it to, this gap is very less if this angle is very less, and typically this angle will be less than 10 degrees. So therefore we neglect this gap, and then I'll equate CB equal to CD, and then I can just say E, and then mark this point as F. Now you look at this angle will be phi 2. This is the secondary, because here I2 will be having the same angle phi 2 with respect to V2. So this angle will be phi 2. Similarly, this angle will be phi 2. So you can just find that. See, these are all triangles. So from manipulating these triangles you can find that. So this is also 90 degrees. So now what is this CE? CE is nothing but I2R2 cos phi 2. So I'll say approximate voltage drop equal to I2 R0 2, and this part CE is nothing but cos of phi 2 plus. Now the opposite of this phi 2 is this one, and this hypotenuse is I2 x0 2. So if I can write I2 x0 2 sine of phi 2. So if I do this, then I'll get this length. This length is nothing but equal to ED length. And if I add it, so this is my expression per voltage drop. So there is no J here, that's what you should notice, because we are just solving it geometrically. Here you should not keep J. So I2 R0 2 power factor plus I2 X0 2 sine of that angle. So this term will give you the voltage drop. And then if I want, now I can say V2 plus voltage drop equal to K into V1. So this also I can use it. So with this, so of course here I cannot know what is angle. So if I use this, see if V2 angle is 0, voltage drop angle is 0, so K into V1 angle. So I will only get the magnitude of the terminal voltage of V1. I will not get this angle. But then this is a shortcut way of calculating. So to just summarize what I have discussed so far, the objective is to go for simplification. So we did that by neglecting the no load current. Therefore, I0 I remove. So I1 is nothing but I2, which I2 dash, which is nothing but K into I2. Then I have this vector diagram. So these voltage vectors of drops I transfer to the secondary side. So I got a drawing like this. The same thing I have redrawn. So this is the table of conversions. If I want to transfer the voltage from secondary to primary, I multiply it by 1 by K. If I want to, so where K is N2 by N1. So this is important. So N2 by N1 is the turns. Also, one more, let me just finish this. So here I have redrawn this, and then now if I look at this larger triangle, I can add the voltage resistance drops and reactance drops separately, and then I'm getting this expression. That is I2 into Z02, and then I'm getting this easier way to find the V1. So I'm getting like this. So finally I got this expression, that is I2 R02 cos of phi 2 plus I2 X02 sine of phi 2, and that will give me the magnitude of the V1. Okay, so this is just a brief explanation. We will try to solve some problems based on this, and we'll try to get some further understanding on this. Before I close this video, just I want to clarify one doubt. See, when I go for ratio, should I take V2 by V1 as equal to E2 by E1? So strictly speaking, this is true when you are neglecting the resistance, but actually it is not true. But then E2 by E1, this will maintain N1 by N2, because the EMF induced is proportional to the number of turns. So EMF induced again proportional to, you remember that EMF equation 4.44 into F into N1 into phi max. So this is what is the EMF induced. So based on this, I can write this part, I can always write it. But then V2 by V1, it will not be this. And then when I equate this to K, so strictly speaking, V2 by V1 is not K, E2 by E1 is K, and V2 by V1, there will be some drops. So just kindly remember this point. Okay, so now we look at one problem. So that is example 23, and it is solve example 21 using the approximate voltage drop formula and obtain V1. So we had solved this problem earlier in lecture 6, and in lecture 7 we revisit this 21 problem, and I want to solve it in a different way by approximate voltage drop formula. So therefore, obviously we'll be ignoring this no load current and all. We'll be ignoring this. Anyway, so let me write. So how do you find? So the objective is to obtain V1. So what is V1? V1 is nothing but V2 plus drop. And what is drop? V2 plus I1 R1 sorry, I2 R0 to cos of phi 2 plus I2 X0 to sine of phi 2. Simple. So all these are nothing but they are not complex numbers. They are just magnitudes. So magnitude of V2, magnitude of I2. So just we do this multiplication and we'll get the magnitude of V1. So this is magnitude of V1 is nothing but this one. So this is what we wanted. So first let's find out R02. So how to find R02? So R02 is nothing but R2 plus R1 dash, which is nothing but R2 plus R1 into K square. So where K is here 1 by 20. So R2 is 0.05 plus R1 is 20 here, 20, and K is 1 by 20. So multiplied by 1 by 20 square. So if I do this, I'll be getting R02. So let's calculate that. So I'll use a simple code here. So R1 equal to R2 equal to X1 equal to and X2 equal to. So let's actually, I'll show you the diagram. So we had solved that earlier, this problem. So 20, 100, so this was example 21. So finally the answer that we got after so many calculations, so much of coding and everything, finally the answer that we got was 9746. So let's make a note of this in our code. So here, so answer is 9746 volts, 9746 volts. But let's see whether we'll get this. So we should get something slightly less than this. Why you can think about it. But okay, now let me go back. So R1 is 20, R2 is 0.05. So I'm sure you will refer to your lecture 6 notes and then follow what I'm trying to do. So this is 100 and this is 0.03, or is it just 0.3? So now let me find R02, that is nothing but R2 plus R1 into K square. So whereas K is nothing but 1 by 20. Similarly, X02 will be equal. Notice that I am not using J for X because I want to, this is a simplified formula, so we are able to get it. So X1 multiplied by K square. So as simple as this. So let me run this. So I got R2 is 0.1 and X2 is 0.55. So I can make a note of this. So 0.1 and then X, this is R02 and X02 is 0.55 ohms. So in our formula, so formula is getting mixed into the rest of the text. So let me highlight the formula. In our formula, I know R02, I know X02. So V2 also we know because V2 is given in the question 400 volts. I2 also I know because I2 is given 180 amperes. So cos phi 2 is power factor, that also I know 0.8. So this also I know. Now just I want to know what is sin phi 2. Okay, so let's see. Cos of phi 2 is 0.8. Therefore, sine of phi 2 is nothing but sine of cos inverse of 0.8. So let's do that. Sine of, in fact, this also you should know it should be 0.6. A cos of 0.8. So 0.6. So this is 0.6. So therefore now I know everything. So I just have to multiply everything. So what is it? So let me just get this formula once again. is something we can do by simple calculator. So V2 is 400 plus, of course, this is kV1, remember. I2 is 180 amperes multiplied by R02 is zero point 0.1 and power factor is 0.8 plus I2 is again 180 amperes plus X02 is 0.55 plus sin phi 2 is 0.6. So this is a simple calculation. So 400 plus 180 into 0.8 into 0.1 plus 180 into 0.6 into 0.55. So 473.8 volts is K into V1. So therefore, so V1 is nothing but, so K into that. So 473.8 divided by K, so that is 473.8 divided by 1 by 20. So which is nothing but 473.8 multiplied by 20. So I'm getting 9476 as the answer. So you notice that we did not use any complex mathematics here. It's just a simple multiplication by k square everything, and I am able to determine 9476. But what is the actual answer? 9746. So it's the same four digits, but just slight reordering. But then this is pretty good. So if you see percentage wise, we are not deviating by so much. So percentage error, if you want to calculate, so 9746 minus 9476 divided by 9746. So how much is that? 9746 minus 9476. So divided by 9746. So it is just 2.7% error. And also this error is 2.7% only because our problem, see this no load current is 1.5 amperes at 30 degrees. So this assumption is also like it has been taken slightly higher side. The no load current for this particular rating and all will be even lesser. So in a practical transformer, that error will be even less than this 2.7%. So, so we have two ways of solving this problem. So here I just solved it in just half a page, whereas in the other example, I had to do all this complicated, I have to find this I2 voltage drop, all these things. So this way we can simplify. So I hope you learned something by solving this, using this simplified voltage drop formula. We'll do some more problems. All right. So after solving the problem, let's look at the next one, that is example 24. And here I have a 230 by 460 volt transformer. Primary resistance is given and reactance is given. And the corresponding values for secondary are also given. Find the secondary terminal voltage when primary terminals are connected at rated voltage and secondary load current is 10 amperes at 0.8 power factor lag. So we'll be using the approximate voltage drop formula here, and we'll be solving this. So you can pause this video, you can try to solve this and match your answer with my answer. So let me do it, my solution. So to begin to answer, first find k. So k is nothing but v2 by v1, so 460 by 230. So this will be actually 2. Now next find r02. So r02 is nothing but R2 plus R1 dash, which is nothing but R2 plus K square into R1, which is nothing but which is nothing but 0. So what is R2? R2 is 0.75 plus and what is R1? So R1 is 0.2. So I'm just searching the numbers from this one. So K square is 2 square. So 2 square into 0.2. So let's see what it is. Oh, I think we have this earlier code. So I'll just modify this, the values, so that I can calculate. So what is K? So K for our problem is 460 by 230. And what are this R1 So R1 is zero point 0.2 and 0.5. Okay. So 0.2, X1 is 0.5. Whereas R2, what is R2? So R2 is 0.75 and 1.8. Okay. 0.75 and 1.8. So this will calculate R02 and X02. So let me just run that. So from this R02 is 1.55 and X02 is 3.8. So this is 1.55 and X02 is 3.8. So I got this R02 and X02. Similarly, I2 value is given. So I2 value is 10 amperes and power factor is also given. That is cos of phi 2 is 0.8 and therefore you know sine of phi 2 is also is actually 0.6. So you know this. So the secondary V2 is not given. So V2 is not given. But then V1 is given. So here it is said the term find the secondary terminal voltage when primary terminals are connected at a rated voltage. That means that is 230 volts. So V1 is 230 volts. And I know what is the formula. So we had just earlier we had used this formula. Same thing. I'll just copy it here. So what is that? So I copy this formula. So now we are doing this for this problem. So I'll just substitute the known values. So K is 2 and V1 is 230 is equal to V2 is unknown and I2 is 10 amperes. R02 we just calculated 1.55. Cos phi 2 is 0.8. I2 is 10 amperes. X02 is 3.8 and this is 0.6. So from all these things only unknown is V2. So I can find V2. So how do I find? So let me just, so 2 into 230, let me just write it directly here. 2 into 230 minus, so 10 into 1.55, I'll just 10 into 1.55 into 0.8 minus again. So because these terms go to the other side, they become minus, minus 3.8 into power factor is 0.6. So by simple calculation, I get 424.8. So V2, I'm sorry, I think I made a mistake. Did I? Oh, correct. 424, nothing. This 420. I was thinking it was 400. So 424.8. So this is the secondary terminal voltage, and that is what is asked in the question, and we have solved it. So what is the expected no load voltage? So V2 under no load is actually 460 volts. So if I don't load it, I'll get 460 volts, and because of the loading, it is there. So if I want to, I'll just introduce a new equation, new formula, that is voltage regulation. So voltage regulation is nothing but voltage under no load condition minus voltage under full load condition or whatever loaded condition divided by voltage under no load condition. So percentage voltage drop we have to find out. So if I want to now find out the voltage regulation, 460 volts is the no load voltage minus 424.8 is the voltage. So divided by 460. So how much is this? So 460 minus 424.8 divided by 460. So voltage regulation is this one. If you express a percentage, it is 7.65%. 7.65% is the voltage regulation. So typically voltage regulation we want to be as low as possible. 1%, 0.5% or 0% is good. So With this, I complete this problem. Let's see more. Okay, so we'll just go back once again and then discuss slightly about this voltage drop and regulation. And this formula that we had written actually applies only for lagging loads. Let me quickly derive another formula for leading loads, but then first let's review this. So you realize like this we have already solved sometime earlier. V2 is the secondary terminal voltage, and to that I am assuming I2 is the lagging current with angle of phi 2. So therefore I2 R2 will come like this. Then leading that will be I2 X2, that is I2 X0 2. So it will be like this, and therefore I'll get the total voltage K into V1 OA represented that. So then what I'm making an assumption is that the length of OA is equal to the length of OB. If I just draw an arc from A to B, so this arc will touch the OB, that is the horizontal axis at OB. But then instead of considering OB as the total exact length of the V1 vector, I am just taking the vertical, like a line which is dropped vertically from A, it meets at B. So this small gap I am just allowing as the approximation. So therefore now to know V1, I can just measure O to D. And O to C is anyway V2. So C to E is I2 R0 to cos phi 2. And E to D is nothing but, uh, I think let's label this as G. So ED is nothing but G into F, which is nothing but I2 X2 sine, because it's opposite to this phi 2. And therefore I'm getting like, so this OC is that one, and then CE is this term. So CE is this term, and then this term is nothing but ED. So like this. So now this all is true when the power factor is lagging and this phi is below. So let's draw the vector diagram. What happens with leading power factor? Leading power factor load. So this is V2 and this is I2. And this is leading by cos of phi 2, leading by phi 2 angle. So now what happens? I'm sorry, I think I should draw a bigger line for V2. So let me extend up to here. So this is V2. So now I want to write I2 or not 2. So that will be like this. So I2 or not 2. And this angle, if I just extend this horizontally, so this angle will be phi 2, the same as this one. So this is I2 or not 2. Now leading that by 90 degrees will be I2 X0. So this will be 90 degrees leading this drop. So this point, if I join to my original origin, this will be K into V1. And then if I drop the vertical from there, now let me start labeling the points. Let's call this OA. So this OA meets here at this point. So let's call this point as B. Let's call this point as C. And let's call this point as D. Then from C, if I drop one vertical, let's call this as E. And then I'll draw one horizontal line here. And let's call this as F. So the angles. So the angles are, so this angle will be phi 2 and this angle is phi 2. So you can, again, you can just through manipulation through all the angles, you can find that. So I'm interested in voltage drop. So what is voltage drop? Voltage drop is nothing but the difference between V2 and V1, kV1. So here the voltage drop is actually dB. So because the horizontal component is this one, so uh, voltage drop is actually K V1 minus V2. So that is nothing but OD minus OB. So OD minus OB is actually negative, so which is nothing but dB. So it turns out that voltage drop is coming negative. It is possible depending on the lens. So dB is what we want to find out. So what is dB? So dB is nothing but uh, ED minus EB. So this is nothing but ED minus BE. So actually the minus sign will come. So anyway, so I'll just take this component. See what is BE? So BE will be I2 R naught 2 cos of phi 2. And then what is FC? It's nothing but, or DE is nothing but I2 x naught 2 sine of phi 2. So everything is same, just that now from here I am going rightwards for this, but then I am coming backwards for this. So therefore the voltage drop will be nothing but this minus this, that is BE minus DE. So this is my voltage drop. So I'll just, so what is BE minus DE? So I just have to do I2 R naught 2 cos of phi 2 minus I2 x naught 2 sine of phi 2. So this is my voltage drop. So if I compare this with the earlier I2 R naught 2 cos of phi 2 plus this one, whereas here this minus this one. So only difference is this plus sign is becoming minus sign. So therefore overall voltage, therefore the final formula for voltage drop, formula or equation for voltage drop is like this. Voltage drop equal to I2 R naught 2 cos of phi 2 plus or minus I2 x naught 2 sine of phi 2. This is my voltage drop. So where plus is for lagging load and minus is for leading load. So you might ask an intelligent question, what happens if the load is neither lagging nor leading? It is a unity power factor. So under unity power factor, sine anyway will become 0. So there is no problem. This term entirely will become 0, and then this will be the voltage drop. Now, just before we conclude, so what is regulation? I just briefly mentioned some time back, voltage regulation. Voltage regulation is nothing but Vreg. Is nothing but, it's a percentage actually. Voltage under full load, sorry, voltage under no load minus voltage under full load divided by voltage under no load. So now voltage under no load minus voltage under full load is nothing but actually the voltage drop. So if this is the voltage drop, so and no load voltage, so I can actually divide this entire thing by no load voltage. So this is nothing but voltage drop by no load voltage is rated voltage V2. So, or actually I should strictly following, I should be using E2 here, but here I'll just use V2. So then if I come back and then just substitute this in this, if I just divide, so I'll be getting I2 R naught 2 by, let me go by E2 only. So E2 or voltage at no load, and then cos of phi naught plus or minus I2 x naught 2 by E2 sine of phi naught. So this is nothing but voltage regulation. So of course you have to convert into percentage. So the problem is here I can define this. What is this? This is actually percentage voltage drop because of the resistance. So let's define as VR cos phi naught, sorry, phi 2 plus or minus, this is percentage reactance drop because of the reactance. So this is nothing but Vx sine of phi 2. So this is my V regulation. So this is the formula for voltage regulation. So what is VR? VR is percentage drop due to resistance. So the combined resistance R naught 2. Similarly Vx. So with this formula I can do that. So based on this we'll quickly solve one problem and you'll get better understanding. So here is that formula. Here is that problem, that is example 25. So calculate regulation of a transformer whose full load resistance drop is 1% and that of reactance drop is 6% when these different power factors are there. Okay, so what we know, the voltage regulation formula, just now we have derived that, is nothing but VR cos phi, phi 2 plus or minus Vx sine of phi 2. So let's take the first case, zero point 0.8 lagging. Because it is lagging, I'll use the plus. Since this VR and Vx values are given, so VR is 1%, they are already in percentage. So my answer also, I'll get it in percentage. Vx is 6%. So voltage regulation is 1% of 0.8 plus 6% of 0.6. So this is for the case A. So how much is this? So let me calculate. 0.8 into 1 plus 6 into 0.6. So I'm getting 4.4% regulation. Now let's take the second case. So power factor is 1. So therefore voltage regulation will be 1 into 1 plus 6 into 0. Because cos phi is 1, sin phi will be 0. So this is nothing but 1%. So even under the unity power factor, the voltage is slightly reducing by 1%. This is a voltage regulation. Now let's take the last part. That is voltage regulation is 1 into 0.8. Here I'll use minus sign because the power factor is leading. So 6 into 0.6. So this will be, so I'll just substitute the minus sign. So I'm getting minus 2.8. Minus 2.8% is the voltage regulation. So the voltage regulation can be positive, it can be 0, it can be negative also. Voltage regulation negative means the terminal voltage is actually more than the induced EMF. That is all on account of the power factor of the load. Because the load is highly capacitive, sometimes as the load increases, the voltage also can increase. That's what we are seeing in this case. But normally the voltage regulation will be positive and it will be usually in a single digit percentage. We don't want the voltage to deviate. So preferably it should be less than 5% for a good performance of the transformer. Let's do some more problems. So this is again an interesting little problem. Try to read this problem and understand what is going on in this problem. It's a kind of nice conceptual problem. These kind of things are very suitable to give in an exam. These kind of problems because unless you understand it, you will not be able to solve it. But let's see. So you can attempt the answer for this problem and you can compare your solution with what I am doing. So let's get started with solving this problem. So what I have is calculate the percentage voltage drop of a transformer whose R02 is 2.5%. First of all, what do you understand by this? What do you mean by R02 equal to 2.5%? So it actually has to be ohms, but why it is given in the percentage? So sometimes the resistance drop of the entire transformer will be given in percentage like this. So how do you interpret this? So this is nothing but, percentage drop is nothing but, what is the full load current IFL? This multiplied by R02 will be the full load resistance drop. This divided by your V2 will be the, or E2 will be the, let me put E2 here, or E2 or V2, like it, because again there is a small difference, so it doesn't difference give that much of error. So this one is actually 2.5%. So this is how you should interpret it. Now this is also nothing but VR, what we have defined earlier. So voltage drop because of the resistance. So therefore this is nothing but small VR. and similarly x naught 2 is 5%. This is nothing but Vx. So that part is good. So next, the rating of transformer 500 kVA, but the load on the secondary is only 400 kVA. So these all VR and Vx are defined for the full load. So here the full load current. So let me write the percentage drop formula. So percentage drop formula is nothing but R naught 2 into I by I full load into cos of phi 2. This is I2 by I2 full load. So this is plus because lagging power factor is there. So x naught 2 percentage, this is again percentage, into I2 by I2 full load into sine of phi 2. So what I'm doing is that how I got this formula. So let me show you. So normally what is a percentage regulation? So percentage regulation is VR into cos phi 2 plus Vx into sine phi 2. But then percentage regulation is only defined at the full load. But now I want at the partial load percentage drop. So that fraction, whatever is my fraction, that fraction I'll multiply like this. So if I do this, then I'll be with this fraction. If I multiply, I'll be getting the formula. So the same thing I have done here. So it's nothing. So this is I2 by I2 full load. If I do like this, so then I can convert the regulation formula into voltage drop formula at a given fraction. Okay, so far so good. Now, what is what I'll do is I'll just multiply both sides. Here I'll multiply with V2, and denominator also I'll multiply with V2. Similarly, numerator I'll multiply with V2 and denominator I'll multiply with V2. So what do I have now? So VR, so percentage drop equal to VR into this whole thing. So what is in the numerator? I2 V2 cos phi 2. This is nothing but P2 divided by, what is this one? V2 into I2 at full load. This is nothing but kVA full load. So cos is gone now. So plus Vx into, what is this one? I2 V2 sine x2. So this is Q2, the reactive power divided by kVA. So like this I'm getting. So now I have to determine, see what is the load? Load is 400 kVA at 0.8 power factor lag. So this is nothing but S2. So S2 is nothing but P2 plus JQ2. So how to get this P2 and Q2? Nothing but 400 into 0.8 plus J into 400 into 0.6, because I'm just converting that. So this is 320 kilowatts because this is kVA, and this is 240 kVAR. So now that I know this, so this part I know, so now I can find the percentage drop. So percentage drop will be, so what is VR? 2.5% multiplied by 320 by total is 400 plus what is, I'm sorry, total kVA is 500. That is the rated kVA given in the question. So if I go up, so this is the rated kVA of the transformer is 500. So that will come here. So plus, now what is the 5% drop multiplied by 240 by 500. So this total will be my answer. So let's calculate that. So 2.5 multiplied by 320 divided by 500 plus 5 multiplied by 240 divided by 500. So I am getting 4. So that is the 4%. So the voltage drop will be the 4% voltage drop. So this is the solution for this question. So in a way it is slightly complicated, but then if you actually write down everything and then analyze it yourself, you will find that it is, fairly intuitive. So try to understand this problem. Thank you.